Just take it away when you're ready.
Okay, thank you, everyone. Thank you, Rita and the organizer, for giving me this opportunity. Okay, so what I want to talk about today is a joint work with Umberto Picchini from Chalmers University in Sweden. And it's a work about try to speed up and accelerate the performance of some sequential approximate Bayesian computation schemes while preserving the accuracy and the feature of the schemes. Okay, so this is our overall work. ABC, so approximate Bayesian computation, is one of the possible approaches within the broad class of simulation-based inference, and our goal is to construct some. Oops. Okay, that was too far. Go back to the beginning. Now our work is to, our goal is to actually contribute to this and improve these sequential ABC schemes. Okay, so within the general class of simulation-based inference, the idea is that there might be some underlying likelihood that is either unknown or difficult to sample from. And the key assumption is just the fact that we have some underlying simulator, or sometimes it's called generator or generative model, which we believe is approximating in a suitable way the underlying true model describing the phenomenon of interest. Okay, so it can be a model as a system of ODEs or SDEs or PDEs, SPDs, depends on what phenomenon you are interested in modeling. It can be something related to climate. What I have in mind are some examples from neuroscience. And in general, it can be anything describing the evolution of some phenomenon of interest across time. Okay, what is the idea? We have this this model that we can code. We have some parameter, and we very bad with this pointer. And what we do is nothing else than getting some parameter theta star and use this generative model to simulate a new set of data, m theta star. And through m theta star, we arrive to a new data set y star. And actually, if we imagine to iterate this procedure for a lot of theta star, so if we imagine that we can sample this parameter theta star and propagate through this generative model, we have a lot of data set, and these data set are observation or sample from the unknown likelihood p of y theta. Okay, so this is the key idea, and the first approximate Bayesian computation scheme that was initially proposed is a very intuitive one. It's called accept and rejection ABC, and it goes along this line. What we do is we sample some initial parameter theta star from our prior. We use our simulator to generate a new set of data y star. Perhaps the dimension of the data is too high because we are dealing with high-dimensional systems. So we, instead of dealing with the whole data set y star, we summarize through some statistic S. And note that S can be the identity function in case we want to deal with the whole data set. Okay. And then the idea is very simple. We have the observed data set. We have the summary of the observed data set. We want to distinguish. We want to decide whether the simulated summaries are close enough to the observed one. Okay. And by close enough, we mean if they are if there's distance is smaller than some quantity epsilon. Now, there is a whole literature on what type of distances we can construct, L2, Wassersteins. There will be someone else talking about other type of distances. Obviously, one has to decide what does it mean close enough, right? What does it mean? I mean, what's the sensible value for epsilon? But the idea is very simple. We sample from the prior, we generate this data. Are my data close enough to the observed one? If yes, I keep the sample particle theta star, otherwise I reject it. Okay, and I repeat that n times, and I have then n observed realization theta star that has been sampled from the prior. Obviously, as you can imagine, this is very intuitive. It can be parallelized. We can do that across the processor that we have, but it's very wasteful, right? Because we are sampling from the prior, and we know that the prior might be quite flat and vast and quite different from actually the region of interest. So there has been quite a lot of work on developing some sampling schemes, some algorithms that work better. They are less wasteful somehow. And among them, I like to mention the sequential importance sampling and sequential Monte Carlo ABC schemes that are based on the idea of having some underlying sequential Monte Carlo scheme, and they are parallelizable, and they are more plug and play than MCMC ABC. So the focus of today's talk is to actually try to improve the existing sequential ABC in a way that I'm going to describe soon. Okay, so by describing, by improving, I mean that, well, if you think about sequential schemes, what they do is you start at a first iteration from the prior, and then you are going to sample from you are going to propose some particles, you perturb them, and you sample from a proposal. But even if these sequential schemes are working better than the acceptance rejection in the sense that they have a higher acceptance rate, especially at the first iteration, as we are sampling from the prior, there can be a lot of waste, a lot of particles that are sampled and then rejected because they are not really close enough to our observed data. So what we would like to do is to actually make this proposal informed by the current data. Okay? So we would like to have some proposal that is actually guided by the data in a way that we are hopefully converging towards the region of higher posterior mass in a faster manner than with the canonical sequential scheme. Okay? So in a way, instead of letting the proposal explore the entire parameter space, that might take some time, we kind of want to give some hint and say, well, actually, it will be useful to be a bit more investigative towards this direction, and we are going to inform the sampler based on the available data. And obviously, we want to do that in a way of speeding up the convergence to the region of higher acceptance rate. So we want to reduce the rejection rate of the particles while keeping the accuracy, right? We don't want to have a sampler that accepts each particle with probability 1, but then we are going to have a very poor performance, right? Otherwise, it doesn't make sense. The overall goal is to have an accurate sampler that is faster than the reference one, and by faster, I mean higher acceptance rate. So let me just give you an intuition of this sequential scheme. But at the beginning, we all sample from the prior. So at the beginning, we have some prior. All particles have the usual weights. And then we have t consecutive iteration. And the idea is to propagate a bunch of particles, capital N, across this iteration. And at each iteration, we are going to have t different ABC posteriors. Okay? And then at some point, we decide to stop. So how does it work? At the beginning, we have our prior. We sample from the prior. So we have the step 1 will be the acceptance rejection ABC. We're going to have a bunch of N particles whose distance between the simulated data and the observed data is smaller than some threshold epsilon 1. Each particle has its own weight, and we use those weights for obtaining the ABC posterior as step 1. Okay? We have these particles, we sample from the particles, we perturb them with a proposal, and then we generate new data and decide whether they are close enough to the reference data. And we iterate this procedure up to some final time. We have a sequence of decreasing threshold, so we want to be more and more restrictive, more and more focus on decreasing the distance, the maximum, the largest possible threshold value that we want to accept between the distance between our simulated and observed summary statistics. And at the final step, we are going to have some procedure that hopefully is going to target is going to be as close as possible to the true unknown procedure. Okay, and there are different ways of considering how to stop. One possibility is to have a sequence of thresholds, so we fix this threshold epsilon1, epsilon t in advance, or another possibility is I let the algorithm evolve until the acceptance rate goes below a certain percentage, like 1.5. So let me just give you an idea of the scheme. This is the sequential Monte Carlo ABC in its form. So in the step 1, we have this acceptance rejection ABC, all particles at the same weights. And then the idea of sequential Monte Carlo is to sample a particle from our accepted particle given some weights, and then perturb them with some sampler. Once we have perturbed the particles, we simulate the data with our generative model. We get the summaries. We decide if the summaries of the generated data are close enough to the summary of the observed data. If yes, we keep the particles, otherwise we reject it. Okay? Every time we do that, we are going to update the weights, and we repeat this procedure until we have n particles. At that point, the iteration is done, and we are going to reduce epsilon, and we move on. Okay? So what I describe here in the for loop is the process that make me move from these particles to this one, and all these particles have the corresponding weights. Okay? So this is the sequential Monte Carlo ABC, and there are different ways of perturbing these particles once that have been sampled, and the most canonical way, the most used one, is actually a Gaussian sampler with some mean and covariance that depends on the accepted particles at the previous iteration. Okay. There are different versions throughout. We are going to focus on the one of Filippi et al., and I'm going to talk about that in a second. And sequential Monte Carlo ABC is considered as the golden standard. It's actually implemented in some software. One of them is also related to Rito, Pi ABC and ABC Pi. So this is kind of the state of art somehow. Okay, so what we want to do is to have a conceptually different step, but practically it's not so bad. So what we want to do is switch the focus from our proposal that depends on the particles accepted at the previous iteration to a proposal that is guided, that is informed by the summaries. Okay, so somehow what we would like to do is to sample from a proposal that depends not only on the particles at the previous iteration, but also on the summaries. Okay, and I'm going to focus not so much on the sequential Monte Carlo ABC, but on the sequential importance sampling ABC, that somehow is simpler to describe and to work with, because it doesn't have this initial step of drawing a particles among the particles kept at the previous iteration with a certain weight. So how does this work? Well, what you have to do is you simply sample a particles based on some proposal. Okay, so what does it mean? If we look at the scheme here, if you imagine to replace this step, what you have is the sequential importance sampling. Okay, so if we just delete this step here. Okay, so in the canonical sequential importance sampling ABC, you have the particles from the previous iteration. You perturb them with some proposal. And I said before that the proposal is typically a Gaussian kernel with some mean and covariance. Okay, now what we want to do is to have some conditioning and switching from a proposal that depends only on the particles at the previous iteration to something that is conditioned on the available information of the summaries. Okay, so the idea is somehow coming from the work of Umberto and the other co-authors. So if you imagine to have theta and s, that is a pair of accepted parameter and summaries, and if we imagine that they are distributed according to some Gaussian random variable with some mean depending on the parameter and the summaries and some covariant metrics, then we can immediately derive the fact that also the conditional distribution of theta given the summaries is Gaussian, right? If we have a joint random variable that is Gaussian, the conditional distribution is also going to be Gaussian, with mean and variance that are given by this expression. Okay? So instead of proposing from a Gaussian sampler depending only on the particles at the previous iteration, we are going to have, well, let's say that we have a Gaussian sampler on the particles and the summaries, and let's use this to derive a conditional proposal sampler of the particle given the summaries. So again, it's going to be Gaussian with this mean and covariance. Okay. Yeah. Okay. We call this one blocked because all particles are sampled in block, in the sense that all particles, all parameters share the same mean and covariance. So all the coordinates of theta are sampled jointly. Okay. This sampler might be mode seeking. So in the paper, we have a few variants to take into account. One idea is to actually come out with a sort of optimized covariant matrix to reduce this. And we also derive some guided scheme for the sequential Monte Carlo, but I don't have time, so I will be happy to talk about that during the lunch break, or actually there are all the details in the paper. We are going to upload the newest version of arXiv most likely next week. So please be, I mean, the version is, I mean, there is already an arXiv version, but next week there will be a most up-to-date one. Okay, I just want to mention, as I know that some people in the audience are interested on copulas, I also want to mention 3 minutes. Wow, okay. So I also want to mention no, I don't want to mention this. Well, okay, let me just say this, that one of the main drawbacks, somehow we have no guarantees a priori that the sampler, that the Gaussian sampler is a reasonable one. So instead of a Gaussian sampler, we propose a copula-based sampler, where the Gaussian assumption of having a normal distribution is replaced by a general copula that can be a Gaussian or a T-copula, and each individual component of theta given S is going to be according to some marginal that are not necessarily Gaussian, but we consider uniform, triangular, and so on. Okay, so we have a few examples. This is the one of twisted, the twisted example, where we know that we have 5 coordinates and 2 of them are highly correlated in the prior. And what we can observe, so the orange line corresponds to the standard non-guided sequential Monte Carlo ABC. The light cyan version is its optimized version. So this is our competitor. Okay, so up to now, the state of art will be to use either the standard sequential Monte Carlo ABC or its optimized version. By optimized, it means an optimized covariant matrix when we sample from this multivariate Gaussian. This is the guided sequential Monte Carlo ABC that we propose. What I'm plotting here is the log Wasserstein distances across different iterations and across 10 independent runs. What do I mean? I run my ABC scheme up to a certain point, so up to the time when the threshold goes below a certain level, and at every iteration, I obtain an approximate ABC posterior, and I compare with the true posterior that I obtain via MCMC. And what I'm plotting there is the log Wasserstein distance. Okay, so the lower is the log Wasserstein, the better it is, because it means that we are close to the true MCMC posterior. And what I want to show you is just the fact that This guy, the sequential Monte Carlo ABC, has a nice log varsians that is smaller than the current state of art. And even those other ones that are the one that we propose based on copulas, in particular this one and this one, immediately have a log varsians sign reaching a very low level, already the iteration 2 or 3, while if we let the state of art ABC, sequential Monte Carlo ABC sampler, we reach this level only after 16 iterations. So that means that they are much faster. I have many more examples to show, but I'm lacking time. So I just want to go to the conclusion. The proposal sampler that we introduced do not really have any overall overhead costs. They are easy to construct, and hopefully they could be incorporated into existing packages. So that would be our hope. And I didn't really have the time to go through all the examples, but we show that actually they are successful in handling different situations like highly correlated posterior or multimodal posterior, cases where neither the summaries nor the posterior looks like Gaussian, models with up to 20 parameter and up to 400 summary statistics, so high dimensional parameter space and or high dimensional summary. We have more to come, and well, the time is over, so thanks for your attention.
Yeah, thanks very much. So I think if anyone has any questions, probably best to ask them over lunch. So I think that wraps up our session. And now it's time for our lunch break. Let's thank our speakers again for this session. And I'll leave it to Vito to say where we're going for lunch.
We have heard a lot about similar terms coming from data assimilation, and then also analytics with the community that speaking. We have covered all the terms, so we can discuss about them on the lunch. So just outside the lunch.
I noticed there's another way to go from the prior to posterior, and you can do tempering in the sense that you get the target and then you squash them, and then you just do this repeatedly with sampling and MCMC. You try that at all?
No.
I use Gaussian is such an unusual. I mean, we live in a non-Gaussian world here.
Yeah. So I mean,
Gaussian seems to be, the broad thing.
overall, the idea of using